Section 11.1, Sequences and their Notation. In this section, we'll write the terms of a sequence given an explicit formula. We'll find an explicit formula given the first n terms of a sequence. We'll write the terms of a recursively defined sequence, and we'll evaluate factorials. So according to a legend, when the game of chess was presented to a king, the king was so amazed that he offered the inventor any reward he wanted. The inventor asked for a single grain of rice to be placed on the first square of the chessboard, 2 on the next, 4 on the next, and so on, with the number of grains doubling with each square. So here's a couple of questions. How many grains were placed on the last square, square 64? And how many grains of rice were placed on the board altogether? Well, we can think about this. There was 1 grain on the first square. The next one would have 2, and each time it doubled. So 4, 8, 16, 32, and this went on until there were 64 numbers in the list. This is an example of a sequence, all right? Each of these numbers in the sequence is called a term. And the notation for a term usually is the letter A with a subscript. So this would be our first term, our second term, our third term, our fourth term, etc. And so to answer question number 1, the question would be, if we kept on going, what would the 64th number in this list be? Let's do a little more formal vocabulary about sequences. So what is a sequence? A sequence is a function whose domain is a subset of the counting numbers. So remember, the counting numbers are 1, 2, 3, ... Okay, so how does that match this example we just did? All right, so there's a function that joins n, the first number, with the first term in the sequence. And so we could probably come up with the formula for the nth term of the sequence pretty easily. If a sub 1 is 1, a sub 2 is 2, you can see that these are the powers of 2. Let's write them down here. This would be 2 to the 0 power, 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power, etc. Okay, and notice that the second term was 2 to the first power, the third term was 2 to the second power, the fourth term was 2 to the third power, and so a formula for the nth term would be 2 to the... Now remember, the power doesn't match the term number exactly, but it's 1 less. So this would be a definition of the sequence. And so why is the domain the counting numbers? The counting numbers refer to the number of the term in each sequence. And so to find what a 64 sub 64 would be, we simply would say, oh, that would be 2 to the 64 minus 1. On the last square of the chessboard, there would be 2 to the 63rd power grains of rice. You can have a finite sequence. So for example, this chess example is a finite sequence. There's going to be 64 numbers in list. Or you could have an infinite sequence. And the way you know you're looking at an infinite sequence is we use 3 dots to continue. It keeps on going. So for example, 1, 2, 4, 8, 16, ... means that it's infinite. It keeps on going. And like we talked about, each term in the sequence is usually denoted with the variable a and then with the subscript. So if we write a sub 4, what this means is the 4th term in the sequence. So using a list of terms or a formula to define a sequence. Question, how many grains of rice were placed on the last square? Square 64. We just already did that actually. We know that there were 2 to the 63rd power. 2 ways to name the first term of a sequence. Often it's used, we use a sub 1 to name the first term of the sequence, and that makes sense because the first term, 1, first term. But sometimes we might call the first term of the sequence a sub 0, You might wonder, well, how am I supposed to know which one I'm using? It'll be clear from the definition of the sequence, but sometimes it's more, we come up with easier explicit formulas if we start the first term with a 0 instead of a 1. But those are just two ways that we often use them. So let's practice writing the terms of a sequence when we're given a formula. Write the first 4 terms of the sequence defined by a sub n equals 2n plus 1. So this literally just means plug in 1, 2, 3, and 4. So if we plug in 1, a sub 1 would be equal to 2 times 1 plus 1, or in other words, 3. A sub 2 would be 2 times 2 plus 1, 5. A sub 3 would be 2 times 3 plus 1, 7. And a sub 4 would be 2 times 4 plus 1, 9. And so the first 4 terms would be 3, 5, 7, and 9. So all you have to do to write down the terms of a sequence are to substitute the first n counting numbers that you're given. Here, you try the next one. Write the first 5 terms of this sequence defined by a sub n is equal to negative 3n plus 5. All right, let's check your work. All right, so we're going to plug in the numbers from 1 to 5 to generate the sequence. If we plug in the number 1, we get negative 3 plus 5, or in other words, 2. If we plug in the number 2, we get negative 6 plus 5. If we plug in the number 3, we get negative 9 plus 5. Plugging in the number 4, we get negative 12 plus 5. And finally, plugging in the number 5, we get negative 15 plus 5. And so this should have been your answer for that one. Now, alternating sequences are sequences whose terms alternate signs. For example, if the first one's positive, the next one's negative, then a positive, then a negative. Or you could start off negative, positive, negative, positive, but the terms will always alternate signs. And you can recognize an alternating sequence because the formula will always contain a negative number, usually negative 1, to some power. Here's an example. Write the first 4 terms of this sequence. And again, all we have to do is plug in 1, 2, 3, and 4. So if we plug in 1, we'll have negative 1 to the first power times 3 times 1 squared, or in other words, 3. That'll be a negative 3. If we plug in 2, we're going to have negative 1 squared times 3 times 4, or in other words, we're going to have 12. So see, the first term was negative, but the next one's positive. When we plug in 3, we'll have negative 1 cubed times 3 times 9, or in other words, negative 27. So the next one's negative. We're expecting a 4th term to be positive. Here, why don't I pause for a second? Find out what the 4th term is equal to. Okay, let's just check. So that would be negative 1 to the 4th times 3 times 16. And again, that's going to be positive 48. So here, why don't you see if you can do this one? Write the first 3 terms of this sequence given this definition. And again, we see that we have a negative number to an nth power, so we know this is going to alternate signs. All right, let's just check your work. So n is equal to 1. We would have 3 times 1 on the numerator and negative 2 to the first power in the denominator. If n is equal to 2, we have 3 times 2 in the numerator and negative 2 squared in the denominator, so that's going to be 6 over 4. If n is equal to 3, we have 3 times 3 in the numerator and negative 2 cubed in the denominator, so that's going to be 27 over negative 8. And so you can see the alternating signs, a negative term, a positive term, and a negative term.